So today we're going to continue looking at the quality of tests. Previously we looked at the type 1 and type 2 errors that might occur when conducting a hypothesis test, but we've only looked at discrete distribution hypothesis tests so far. Now we're going to move over and look at continuous distribution hypothesis tests, particularly the normal distribution, the X-bar sample mean hypothesis test. When we looked at finding the probability of a type 1 error, we recognized that we were finding the critical region, and from the critical region we would find the probability of the critical region occurring. Now the critical region, the intention is for it to match as closely as possible to the significance level. So if we set a significance level of 5%, we want a critical region of 5% or close to 5%. With a discrete distribution, it's difficult to get that exactly on our significance level because we're either choosing one of the discrete values or the consecutive discrete value, and rarely do any of them land exactly on 5%, 1%, whatever we like. Let's have a think about this distribution here. X follows a binomial distribution where n is 10 and p is 0.2. If we're trying to find the critical region at the upper end, we can check the probability that x is greater than or equal to 5. We get 3.28%. This is too small, so we'll check the probability that x is greater than or equal to 4, and we get 0.1209. These are the closest we can get to 5%. We either have to go with 12.09 or we go with 3.28. Usually we'll go with the one that's smaller. My point is, we can't hit 5% exactly, even though that was our significance level. This will rarely happen with a discrete distribution. With a continuous distribution, though, we don't have the same restriction. We're able to choose an exact value for our critical value, for our boundary value, based on the probability below or above that value. Let me use the normal distribution to remind you about this. So here's a normal distribution where the mean is 50 and the standard deviation is 3. If I wanted to find a value that has 5% above it, I can make use of the inverse function. I can find the exact value that has 5% above it. I'll go for the inverse normal distribution function. I'll put in the probability below, the area below, which is 0.95, standard deviation of 3, and the mean of 50. And my calculator will give me an exact value. Well, a decimal value, but an accurate decimal value. This gets us 54.9346. So to 4 decimal places, this is a value that has exactly 5% above it. This time round, my critical region, x being greater than 54.9346, would match my significance level. We can't quite get there with the discrete, but we can with the continuous distributions. So this is a major point for you to recognize, and your understanding of this will be built in to the questions that you work with throughout this topic. And your understanding of this is going to be assessed and is going to be tested by the examiner, maybe in a subtle way, maybe in a more conspicuous way. But this will be a running theme through the questions that are set for you. Do you appreciate the difference between the discrete and the continuous distribution? Okay, let's look at an example question where we're working with the type 1, the type 2 errors, and a continuous distribution. Here we've been told that the weight of jam in a jar, measured in grams, here we're told that the weight of jam in a jar, which is measured in grams, is distributed normally with a mean of 150 grams and a standard deviation of 6 grams. So just in that first sentence, we should already know we have a normal distribution, just talking about the weight of jam in any particular jar that might be chosen. So let's state that distribution. X follows a normal, the mean is 150, standard deviation is 6. If we continue reading, we're told the production process occasionally leads to a change in the mean weight of jam per jar, but the standard deviation remains unaltered. The mean weight can potentially be a variable. That's our first indication of what to do. Let's continue reading. The manager monitors the production process and for every new batch takes a random sample of 25 jars. So now we have a sample size, we have a value for n, and weighs their contents to see if there's been any reduction in the mean weight of jam per jar. So plenty of indications here that we're going to be working with the X-bar distribution. We have a value of n, and we've been talking about the mean weight. That's what the X-bar distribution represents, the mean weight of a particular sample. After that, we're told anyway to find the critical value for the test statistics X-bar, which is the mean weight, in a sample of 25 jars. First using a 5% level of significance, and then using the 1% level of significance. Okay, so let's get down the X-bar distribution. We know that the mean is always going to match between the X and the X-bar. The standard deviation or the standard error, that is going to be sigma over root n. So in this case, it's going to be 6 over root 25. That can be simplified, and the value will be put into our calculator, 6 over 5. So I'm definitely just going to rewrite this. We know square root 25 in our heads. I'm definitely going to rewrite this, and this is what we're going to be using in our calculators when necessary. Okay, so let's look at working with the 5% level of significance. So this is a hypothesis test. What would the hypotheses be? Null hypothesis is that mu equals 150. The alternate hypothesis, which can read back through the question, the manager was monitoring the process to see if there had been a reduction in the mean weight of jam per jar. So mu is less than 150. Okay, we're working with the distribution we've already stated. A diagram is going to be really useful here. We know that the mean value is 150, or that's the mean X-bar value, the central, the median X-bar value, and the median Z-score is going to be 0. We're interested in this value right here, the value that has 5% below it. We don't know what the X-bar value is, but we do know a Z-score that has 5% below it, negative 1.6449. Now you can find this with the inverse function on your calculator, or we can use the tables and we'll just pull up that value from the written tables. We need to find this X-bar distribution. This is the critical value. This is what we're going to use for our critical region. Something that links the Z-score and the X-bar value, something that links the Z-score and the real-world mean value is the standardization formula. Z equals X-bar minus mu over sigma over root n. X-bar is our critical value, so we can go ahead and make that the subject. We can rearrange by multiplying through by the denominator and adding on mu. And then we can just substitute our actual values in there. So the negative 1.6449, 6 over 5, and add on 150. Altogether, this is going to give us our critical value, and the critical value is 148.0261. Now, I've given this the 4 decimal places because we're now entering a realm of statistics where the accuracy really matters. 0.0261 would usually seem insignificant. It's quite a small proportion of this number. But actually try the rest of the question using just 148 rather than the whole value, and just see the difference it makes to your answers. Okay, so we've used the formula here. We could have used the inverse function on our calculator. Because we know the standard deviation and the mean, we actually have enough information to use the inverse function on the calculator. We could have said inverse 0.05, standard deviation, mean, and we would have got exactly the same answer. So you do need to be comfortable enough to use both the formula and the calculator. If the question had an unknown value of n or an unknown value for sigma, the calculator will not be able to help you. Examiners are going to throw in questions that are testing your comfortability with this formula as well. Okay, and from here we can find the critical region. So it's going to be any X bar value, any result of X bar, which is less than 148.0261. Now, the probability of a type 1 error, if you've got the main point in the introduction to the video, you'll realize the probability of this critical region is going to be 5%. So usually you'll just be asked to state the probability of the type 1 error, because without doing the calculation, you should know for a continuous distribution, the significance level is going to be the probability of a type 1 error. If you don't believe us, you can go ahead and do that calculation for yourself. Part B is looking at the 1% level of significance. So we're going to go through a similar process. We're just instead focusing on a critical region that has a size of 1%. So the hypotheses would have been the same, and we're still working with the same distribution. So let's get straight to the diagram. So the diagram in the region, the critical region, this left-hand side, we only want there to be 1%. For the X bar values, we know that the middle, the median, mean is 150. We know for the Z score, this is 0. We want to know the X bar value that corresponds with 1%. That corresponds with having 1% below it. The Z score that matches is negative 2.3263. Once again, we'll use the standardization formula. We'll rearrange it first before substituting. Our critical value is going to come from Z multiplied by sigma over root n plus the mean. We're basically doing the same substitution as we did before, but this time round the Z score is negative 2.3263. When we put all of that through, we get a critical value of 147.2084. And that leads to a critical region where X bar is less than or equal to 147.2084. So once again, we could have done the inverse on our calculators. You have the choice of which one you're going to do. This leads to a critical region where X bar is less than or equal to 147.2084. Now in part C of the question, there's some additional information. We're told that the true value of mu for the new batch is in fact 147. And we're asked to find the probability of a type 2 error for each of these two situations. The 5% level of significance, the 5% critical region, and the 1% level of significance, the 1% critical region. So let's start with the 5%. Remembering that the probability of a type 2 error is going to be the probability of the acceptance region, so the complement of the critical region, the opposite of the critical region, calculating that using the new parameter. So the probability that X bar is greater than 148.0261 using mu equals 147. So this can just go into our calculator. NCD, our minimum is that critical value we'd found. Our maximum is going to be 1000. We can choose any arbitrarily large number. Standard deviation 6/5 and the mean of 147. So the probability of a type 2 error, 0.1963. Similar thing for the 1% critical region. This time round, the complementary area or the acceptance region is going to be X bar is greater than 147.2084. And we're going to calculate the probability of that using mu equals 147. Very similar calculation. We're changing our minimum value to 147.2084. This should lead to a larger answer. So a little sense check here. And we get 0.4311. So here we pulled together some concepts and techniques from a range of different mathematical topics. We've gone to straight maths, looking at the distribution of the sample mean, the X bar distribution. We've pulled the standardization formula in. We're using the inverse function for the normal distribution. We're looking at critical regions. And just from our last lesson, we're looking at type 1 and type 2 errors. So here's where your mathematical proficiency and prowess needs to be on show. Demonstrate that you are actually competent with a range of different skills being used and put together into a new topic. Okay, so that'll be us for today. Moving forward, we'll look at a couple more attributes of the quality of a hypothesis test. We'll be looking at the size, we'll be looking at the power, and we'll be looking at the power function.